All right, welcome. So now we're going to start section 1.2, which is Euler circuits and the Chinese postman problem. In the first section, we created a graph of the Königsberg bridges and asked whether it was possible to walk across every bridge once. Because Euler first studied this question, these types of paths are named after him. So the definition of an Euler path is a path that uses every edge in a graph with no repeats, which means you're not going to trace over any of the edges more than once. So being a path, it does not have to have, it doesn't have to return to the starting vertex, right? So a path, right, is just between two distinct vertices, okay? So it doesn't return to the initial starting vertex, okay? So if you look at example 3 here, it says in the example below, okay, in the graph shown, there are several Euler paths, right? So one path is to start at C, right? And you can go C to A, and then A to B, and then B to D, right? So let's trace this out here. And then D to C, and then C to B. Okay, so that would be one path. Okay. We could have another path, right? We could go from A to C. Nope, that won't work. Hold on. We could go, we could go from B, oops, B to A to C, and then to D, and then to B, and then to C. That would work too. Okay, so as long as we trace each edge only once, then we have an Euler path. So each graph may have multiple graphs. Okay, an Euler circuit. Okay, so an Euler circuit is a circuit in which every edge in a graph with no repeats. So in a circuit, the only difference is you do return to the same vertex. So the beginning vertex and the ending vertex are the same. So where you start and where you finish is at the same vertex. So an Euler circuit is a circuit, right? So the definition of a circuit but it uses every edge in a graph with no repeats. Okay, so let's see here. So we could go from all the way around. We could see if we have one of those or not. Okay, so we got, okay, so we looked at Euler circuits. So here, if we look at example 4, here's the graph. Let's see, we could have in fact, here's an example of a circuit, right? So you start with A, right? And then what do? They go to, so here they started with A, right? And so you can go from A to E, right? So they go from A to E, and then to C, and then back to A, and then down to B, then across to C, and then F, and then E, D, and then back to A where we started. So that would be one circuit. That's not the only circuit. Okay. In fact, we could go the opposite direction, right? We could go in reverse order, and that would be also another circuit. Okay. Um, now, it says, here, look back at the examples used for Euler paths. Does that graph have an Euler circuit? So if we look at this graph here, does it have an Euler circuit? Is it possible to go all the way back without retracing any of these? Okay, well, we could look at it for a while, and it doesn't seem like there's a way to do it, right? Because if I start, let's say if I start at B, well, actually, no, no, you can't, because if I start at B here and I go up here and then down here, um, yeah, I'm going to end up going over BC twice. Okay, so it doesn't seem like you can have an Euler circuit with this one, so which is interesting. Okay, so it says a few tries will tell you no, that graph does not have an Euler circuit. When we were looking with the shortest paths, we were interested in the optimal path. With Euler paths and circuits, we're primarily interested in whether an Euler path or circuit exists. It may not be the shortest path, but we're really interested in the existence of a path or circuit. Okay. Now, why do we care if an Euler circuit exists? Think back to our housing development lawn inspector, the lawn inspector from the beginning of the chapter. Okay, the lawn inspector is interested in walking as little as possible. The ideal situation would be a circuit that covers every street with no repeats, right? That's an Euler circuit, right? So if you park your car, let's say the inspector parks her car at one of the corners, right? And so you want to be able to walk the neighborhood and come back to your car at the end, right? And you want to do as little walking as possible. So you don't want to repeat walking up and down streets if you can help it. Okay. Now, luckily, Euler solved the question of whether a graph has an Euler circuit or not. So the question of existence, right? His key insight was that if such a circuit exists, then every time the circuit visited a vertex, it must also exit the vertex. This tells us that as we travel the circuit, each time we visit a vertex, we use up, in a manner of speaking, two edges. Okay? So one going in and one going out, because remember, you can't use the same edge to go in and out, right? That defeats the purpose, goes against the definition of an Euler circuit or path, right? And we can continue doing this as long as there are no vertices of odd degree, right? So if there's a vertex of odd degree, then we would go in, but would then have to repeat an edge to go out. And this gives us the following result. The Euler's circuit theorem. And it states a graph will contain an Euler circuit if it is connected and all vertices have even degree. Okay, so let's repeat that. Euler circuits, right, theorem, the Euler's circuit theorem says a graph will contain an Euler circuit if it is connected and all vertices have an even degree. So that's how we know whether one exists or not. So now let's look at example 5. It says in the graph below, right? Okay, in the graph below, vertices A, C have degree 4, right? So this has, let's just go through them, right? So B has a degree 2, right? A has degree 4. C also has degree 4. But look at D. D has a degree 3, and E has a degree 1, okay, which is odd. So now, so in this graph, what does Euler's circuit theorem say? Well, based on this graph, this does not contain an Euler circuit. It contains an Euler path, right? Because remember, you don't have to begin and end with the same vertex, right? In a path, right? So in this case here, it's connected, right? All the vertices are connected. And so you have an Euler path. Okay, so you can find a lot of them, but it does not contain an Euler circuit. Okay, now we can use similar reasoning to develop a criteria for whether a graph has an Euler path. If such a path exists, then each time we visit a vertex, we would again use up two edges. The only exceptions would be the starting vertex and the ending vertex, which would not necessarily which are not the same, right? They would necessarily have an odd degree, right? Because you're going in, but you're not coming out, right? That's where you're stopping. So you only need an edge going to them. So you'd have an odd degree. Now, and if there are more than two vertices with odd degree, then the graph cannot have an Euler path. So you have to have exactly two vertices of odd degree. So Euler's path theorem, it states this: a graph will contain an Euler path if it is connected and has exactly two vertices of odd degree. Okay, so there's the two criteria: connected and exactly two vertices of odd degree. Now, moreover, the path will start and end, they'll start at one of the odd vertices and end at the other odd vertice, right? That's obviously a condition too, right? Based on the theorem. All right, so let's look at example 6. Okay, so in example 6, it says here, if we look at these here, so look at this has 2, right? Are there any, okay, well, let's just see how many have odd degree, right? So here's 1, okay, and here's 2. What else? Here's another one. So look at that. So this does not contain exactly 2, right? I mean, obviously these highlighted ones, in fact, all the highlighted ones have an odd degree, right? And since there are more than 2 vertices with odd degree, there are no Euler paths or Euler circuits in this case, because remember, to have an Euler circuit, you would have to have all of them with even degrees, right? And be connected. But if you have exactly 2 odd degree vertices with odd degree and it's connected, then you have the existence of an Euler circuit, but not the existence of an Euler path, but not an Euler circuit. In this case, you have neither. Okay. All right, so let's look at example 7 here. So if we look at this graph here, it says, oh, by the way, snow plowing, right? So here, when it snows in the same housing department, the snow plow has to plow both sides of every street. So we can look at how that would work by doubling up the edges, connecting each intersection. Okay, so again, for simplicity, we're going to assume that the plow is out early enough that we can ignore traffic laws, and we're going to drive down either side of the street in either direction. Okay, so we're going to allow that to be the case. This can be visualized in the following graph. Okay, so notice how there's two edges connecting each vertex. Okay, now if we look at each vertex, this one has 4, this one has 6, okay, this one also has 6, and this one has 8, and the next one has 6, and 6, 4, 4, 4, 4, 6, 8, 6, 6, 4, 4, 8, 4. So they all have even degrees. So this is a connected graph, and it has all the vertices have even degrees. So this, then what this tells us is that by the circuit theorem, Euler's circuit theorem, that this graph does contain an Euler circuit. Okay, now we know how to determine if a graph has an Euler circuit, but if it does, how do we find one? For small graphs, we can basically use it, we can do it by inspection, right? So it's usually possible to find an Euler circuit just by pulling out your pencil and then trying to find one by tracing over the edges, okay? But for much larger ones, right, for larger ones and more complex graphs, we need an algorithm, right? So again, an algorithm is a step-by-step process for solving a problem. So we need some sort of process on how we're going to solve and find these circuits, right? So we need to find an algorithm. Okay, so these allow us to solve problems in a systematic way. Okay, or obviously we can use computers then. So so what we're going to do is we will study a number of algorithms in this chapter. And the first one we're going to study is the Fleury's algorithm. Okay, so the Fleury's algorithm is a way of finding an Euler circuit. And here's the steps. Okay, step 1, start at any vertex if finding an Euler circuit. So if finding an Euler path, start at one of the two vertices of odd degree. Remember, it's got to be, the starting point's got to be one of those, right? So if it's a circuit, start at any vertex. If it's a path, make sure you start at one of the vertices that has an odd degree. Then 2, choose any edge leaving your current vertex, provided deleting that edge will not separate the graph into two disconnected sets of edges, right? So we want to make sure that connectivity is protected, right? And then 3, add that edge to your circuit and delete it from the graph. And then 4, continue until you're done. Okay, so let's look at the graph here. So let's find an Euler circuit on the graph using Fleury's algorithm. So what do? Well, they started with A, right? You start with A, and then you go to D, and then you deleted that one, right? And so once we delete it, it's still connected, right? Now we're at D. Now we look at D to E, D to C, and D to B. Okay? And so which one of those can we delete? Well, if we delete DC, then we don't have a connected graph anymore. Okay? So we leave that one alone. But what if we delete DE? Okay? So this one we can't delete because then we'll have a disconnected graph. But if we delete this one, we'll still be good because now we end up with this. Right? And now, okay? And so now, what do we have? Our circuit. So right now here, we have ADE, right? So choosing D, now we have ADE. And now at this point, we can see what our circuit is going to be because we go ADE, and now we can see that it's going to be BDCA because there's no other paths to go. Okay, because each one of these only has one edge going in and one edge going out. Okay, and that's it. So then that's how you find that's using Fleury's algorithm to find an Euler circuit. Okay, so now let's look at this one here. Let's look at this one. So what we're going to do is we're going to see if this has an Euler circuit. So again, if we look at each of the vertices, right? So this one has 2. This is a degree 4. Degree 4. 2. 4. 4. 4. So they all have even degrees. So guess what? There is an Euler circuit. It does exist. So let's find one. Okay. That's going to be a little tougher, right? Because there's a lot of vertices here. So let's start at any point. Okay, so let's start at G. I'm just going to start at G. Okay, so let's start at G and let's go to E. Okay, now we can delete this one. We're using it once, so we'll delete it. Now we're at E, right? So we can either go here or we can go here. Does going either route affect the connectivity of the graph? So we got 3, actually. EB, ED, and EF. Okay, so let's do E. Let's do EF. Or no. Nope. If we do EF, yeah, we could do that. Let's do EF. Okay. And now we can't do EG because then we have a disconnected graph, right? So what about FC? Um, no, that'll work because we'll still have a connected graph, right? Because if we delete these here, we still got a connected graph, okay? And then now we're at C. So let's then go to, now, okay, so let's see here. Well, we can't go this way because then we'll have a disconnected graph. So let's go this way. Let me do it a different way here. Okay, so if we scribble this one out, right? So we're going to scribble this one out, right? And then we went down this way. Oops. Okay, and if we go down this way, let's scribble this one out, right? Okay, so now we still have a connected graph, right? So if I go to D, let's say, if I go to D and I scribble this one out, right? Well, what's left over? I still have a connected graph, right? I still have a connected graph. And if I go to B, right, and I do that, if I get rid of that one, I still have a connected graph, and I can see now you might be able to see the path, right? So if I go this way, so if I go from there, if I go here, here, and then up, and then over, and then down here, and then to F, and then now back to G. So that would mean that my circuit would be G, E, F, C, D, B, A, C. Oh, hold on a second. Oh, I messed up. G, E, F, C. No, it's each path only once. Right. No, this is right. That's good. Yeah. We can visit the vertices more than once. So yeah, G, E, F, C, D, B, A, C, B, E, D, F, G. Yeah. G, E, F, C, D, B, A, C, B, E, D, F, G. I believe that's right. All right, and we will stop there.